Space is big, really big. It's hard to even imagine how vast the universe truly is. There are more stars in the universe than grains of sand on all the beaches on Earth. And that's just the stars. But here's the thing about the universe. It loves to whisper its secrets. We can't always see what's out there, at least not with our eyes alone. Luckily, the universe speaks to us in other ways, through waves of energy. And one of the most important ways we listen to the universe is through radio waves. Now, when you think of radio waves, you might think of your favorite music station or maybe a podcast. But radio waves are much more than that. They're a type of light, just like the light we see with our eyes. The difference is that our eyes can only see a tiny sliver of all the light that's out there. Radio waves have much longer wavelengths than visible light, which means they can travel through things that block visible light, like gas and dust clouds. And that's incredibly important because space is full of gas and dust. Think of it like this. Imagine trying to look through a thick fog. You wouldn't be able to see very far, right? That's what it's like for astronomers trying to study the universe with just visible light. But radio waves can cut through that fog like a beacon. They allow us to see what's hidden behind the cosmic curtains of gas and dust. To listen to these cosmic radio waves, we use radio telescopes. These are giant dishes that collect radio waves from space. The bigger the dish, the fainter the radio waves it can detect. Radio astronomy has revolutionized our understanding of the universe. It's like putting on a special pair of glasses that reveal a hidden world, a world that was always there but invisible to our eyes. We've discovered incredible things through radio astronomy, pulsars, which are rapidly spinning neutron stars that emit beams of radiation, quasars, which are incredibly bright and distant objects powered by supermassive black holes, and even the faint afterglow of the Big Bang itself, known as the cosmic microwave background radiation. By studying these radio waves, we can learn about the birth and death of stars, the formation of galaxies, and the evolution of the universe itself. It's like listening to the universe's own history, told through the faint whispers of radio waves that have been traveling through space for billions of years. And the most exciting part, we're just getting started. As technology improves, we're able to build even more powerful radio telescopes that will allow us to listen to the universe's whispers with greater clarity than ever before. Imagine trying to understand a conversation in a language you don't speak. It would be frustrating, right? That's kind of what it was like for astronomers before we started listening to the universe with radio waves. We could see the stars and galaxies, but we couldn't fully understand what they were telling us. It was like looking at a beautiful painting without knowing the story behind it. Radio waves provide a whole new way of understanding the universe. They allow us to hear the cosmos, to tune into the conversations happening between stars and galaxies. It's like suddenly being able to understand the language of the universe, to decipher the secrets hidden in the faint whispers of cosmic radiation. So what exactly are radio waves? How do they work and why are they so important to us? Well, they're a type of electromagnetic radiation, which means they are waves of energy that travel through space. These waves move at the speed of light, which is about 299,792 kilometers per second. That's incredibly fast. Light itself is a form of electromagnetic radiation, but our eyes can only detect a tiny portion of it, the visible light spectrum. This spectrum includes all the colors we can see, from red to violet. However, there is so much more beyond what our eyes can perceive. Radio waves, on the other hand, have much longer wavelengths than visible light. This means they can travel much farther and penetrate through various materials. Think of it like this. Imagine you're standing on the shore of an ocean. The waves that you see crashing on the beach are like visible light. They have a relatively short wavelength and high energy. These waves are powerful and energetic, just like the light we see with our eyes. But beneath the surface there are much larger, more powerful waves rolling in from the deep ocean. These waves are not as easily seen, but they carry a lot of energy and can travel great distances. These waves have a longer wavelength and lower energy, but they can still carry a lot of information. This is similar to how radio waves work. Radio waves can transmit data over long distances, making them essential for communication technologies like radio, television, and mobile phones. These waves are like the deep ocean waves, carrying information across vast distances and through various obstacles. They are a crucial part of our modern world, enabling us to stay connected and informed. Without radio waves, many of the technologies we rely on every day would not be possible. They are truly the invisible threads that weave our world together. So next time you use your phone, watch TV, or listen to the radio, remember the incredible waves of energy that make it all possible. Radio waves are a testament to the power and wonder of electromagnetic radiation. One of the amazing things about radio waves is that they can travel through space for vast distances without being absorbed or scattered by dust and gas. This is because their longer wavelengths allow them to pass through these obstacles relatively unimpeded. Visible light, on the other hand, is easily absorbed and scattered by interstellar dust, which is why it's difficult to see distant objects in the universe with optical telescopes alone. This ability to penetrate dust and gas makes radio waves incredibly valuable for studying objects and regions of space that are hidden from view in visible light. It's like being able to see through walls, revealing the hidden structures and processes that shape the universe. Radio astronomy has allowed us to peer into the hearts of distant galaxies, revealing the supermassive black holes that lurk at their centers. These black holes are invisible to optical telescopes, but they emit powerful radio waves as they devour matter. We've also discovered strange and wonderful objects like pulsars, which are rapidly spinning neutron stars that emit beams of radio waves like cosmic lighthouses. And we've detected the faint afterglow of the Big Bang itself, known as the cosmic microwave background radiation, which provides a snapshot of the universe as it was just 380,000 years after its birth. Every object in the universe emits radio waves at specific frequencies, creating a unique spectral fingerprint. By analyzing these fingerprints, astronomers can determine the chemical composition, temperature, and motion of celestial objects. For example, by studying the radio emissions from a distant galaxy, we can learn how many stars it's forming, how fast it's rotating, and whether it's moving towards or away from us. It's like listening to a cosmic orchestra, with each object playing its own unique tune. By analyzing the symphony of radio waves coming from the universe, we can begin to piece together the grand story of its evolution. Radio astronomy is a bit like detective work. We're constantly searching for faint signals hidden among a sea of cosmic noise, but with each new discovery, we gain a deeper understanding of the universe and our place within it. And as technology continues to advance, we can look forward to even more groundbreaking discoveries in the years to come. The universe is full of secrets, whispering to us across the vastness of space. And with radio astronomy, we're finally starting to listen. Imagine trying to have a conversation at a rock concert. It's loud, chaotic, and everyone's talking over each other. Now imagine that the concert is happening billions of light years away, and instead of music, it's the faint whispers of radio waves from distant galaxies. That's the challenge astronomers face when they try to listen to the universe. Space is full of radio noise, from our own planet, from the sun, and from a countless number of celestial objects. Sifting through all that noise to find the faint signals we're looking for is like trying to find a needle in a haystack the size of the solar system. But just like a good detective can pick out a single voice in a crowded room, astronomers have developed incredible techniques to isolate and amplify the faintest whispers from the cosmos. One of the biggest challenges in radio astronomy is separating the signals we want to study from all the background noise. This noise can come from a variety of sources, including human-made interference like radio and television broadcasts, as well as natural sources like the sun and other celestial objects. To overcome this challenge, astronomers use sophisticated signal processing techniques to filter out unwanted noise and enhance the faint signals they're looking for. Think of it like adjusting the equalizer on your stereo system. By boosting certain frequencies and attenuating others, astronomers can isolate the specific radio waves they're interested in, much like you can adjust your stereo to focus on the vocals or the bass line in a song. It's a delicate balancing act, but it's essential for making sense of the faint whispers from the cosmos. Another challenge in radio astronomy is the sheer size and complexity of the instruments required. Radio telescopes need to be incredibly large to collect enough faint radio waves from distant objects. The bigger the dish, the more sensitive the telescope. But building and operating these massive structures can be incredibly expensive and technically challenging. Imagine trying to build a giant satellite dish that's hundreds of meters in diameter and perfectly smooth to within a fraction of a millimeter. That's the level of precision required for modern radio telescopes, and it requires cutting-edge engineering and a lot of ingenuity. But the challenges don't stop there. Once we've built a powerful radio telescope and filtered out the noise, we still need to interpret the signals we receive. Radio waves from space arrive at Earth as a jumbled mess of frequencies and intensities, and it takes a lot of computational power and scientific expertise to make sense of it all. It's like trying to solve a giant cosmic jigsaw puzzle, with each piece representing a different frequency or intensity of radio waves. By carefully analyzing these pieces and putting them together, astronomers can gradually build up a picture of the object or phenomenon they're studying. Despite these challenges, radio astronomy has revolutionized our understanding of the universe. It's allowed us to see through the obscuring dust and gas that shrouds many celestial objects, revealing hidden galaxies, star-forming regions, and the remnants of supernova explosions. We've discovered pulsars, quasars, and other exotic objects that emit powerful radio waves, providing clues about the extreme physics at play in these environments. And we've even detected the faint afterglow of the Big Bang itself, known as the cosmic microwave background radiation, which provides a glimpse into the universe's earliest moments. As technology continues to advance, we can look forward to even more groundbreaking discoveries in radio astronomy. New generations of radio telescopes are being built with unprecedented sensitivity and resolution, allowing us to probe deeper into the universe and study fainter and more distant objects than ever before. We're also developing new data analysis techniques that use artificial intelligence and machine learning to sift through massive amounts of data and identify subtle patterns and signals that would be impossible for humans to detect. The future of radio astronomy is bright, and we can expect many more exciting discoveries in the years to come as we continue to listen to the faint whispers of the cosmos. So far, we've talked about how radio waves can penetrate the cosmic curtains of gas and dust, allowing us to see things that are hidden from view in visible light. But what exactly are we seeing with these radio waves? What stories do they tell us about the universe? Well, it turns out that different objects in space emit radio waves at different frequencies and with different patterns. It's like each object has its own unique radio signature, its own cosmic fingerprint. By studying these signatures, we can learn a lot about the nature of these objects and the processes that power them. Let's take a closer look at some of the most fascinating objects in the radio sky. One of the most remarkable discoveries in radio astronomy was the detection of pulsars in the 1960s. Pulsars are incredibly dense, rapidly rotating neutron stars that emit beams of radiation from their magnetic poles. As a pulsar spins, its beams sweep across space like the beam of a lighthouse. If Earth happens to be in the path of one of these beams, we detect a pulse of radio waves at regular intervals. The regularity of these pulses is astonishing. Some pulsars spin hundreds of times per second, and their pulses are so precise that they rival the accuracy of atomic clocks. By studying pulsars, we can learn about the extreme physics of neutron stars, the remnants of massive stars that have exploded as supernovae. Another intriguing class of objects that emit strong radio waves are quasars. Quasars are incredibly luminous and distant objects, powered by supermassive black holes at the centers of galaxies. As matter falls into a supermassive black hole, it gets heated to extremely high temperatures and emits intense radiation across the electromagnetic spectrum, including radio waves. Quasars are so bright that they can outshine entire galaxies, even though they are billions of light-years away. By studying quasars, we can learn about the growth and evolution of supermassive black holes and their role in the formation of galaxies. Perhaps the most profound discovery in radio astronomy was the detection of the cosmic microwave background radiation, often called the afterglow of the Big Bang. The CMB is a faint glow of microwave radiation that permeates all of space. It was emitted about 380,000 years after the Big Bang, when the universe had cooled enough for atoms to form. Before atoms formed, the universe was a hot, dense soup of charged particles, and light couldn't travel very far without being scattered. But once atoms formed, the universe became transparent to light, and the CMB was free to travel through space. By studying the CMB, we can learn about the conditions in the early universe and test our theories of cosmology. The CMB is remarkably uniform in all directions, indicating that the early universe was incredibly smooth and homogeneous. However, there are tiny temperature fluctuations in the CMB, on the order of 1 part in 100,000. These fluctuations are thought to represent the seeds of galaxies and galaxy clusters, the tiny density variations that gravity would later amplify over billions of years. By studying the pattern of these fluctuations, cosmologists can learn about the fundamental properties of the universe, such as its age, composition, and expansion rate. The CMB is a treasure trove of information about the early universe, and it continues to be a major focus of research in cosmology. Radio waves have revolutionized our view of the universe, revealing hidden objects, unveiling the secrets of distant galaxies, and providing clues about the universe's earliest moments. As we continue to build more powerful radio telescopes and develop new techniques for analyzing radio data, we can expect even more exciting discoveries in the years to come. The universe is a symphony of cosmic whispers, and with radio astronomy, we're just beginning to listen. For centuries, humans have gazed up at the stars and wondered if we are alone in the universe. The night sky, with its countless stars, has always been a source of fascination and mystery. Ancient civilizations built monuments aligned with celestial bodies, and early astronomers meticulously charted the movements of planets and stars. This curiosity has driven us to explore the cosmos, seeking answers to age-old questions. Is our planet, with its teeming life and vibrant ecosystems, a cosmic fluke? Earth is a unique oasis in the vastness of space, teeming with diverse forms of life, from the deepest oceans to the highest mountains. The delicate balance of our atmosphere, the presence of water, and the perfect distance from the sun have all contributed to the flourishing of life. But is this rare combination of factors unique to Earth, or could it be replicated elsewhere in the universe? Or are there other worlds out there, perhaps even other civilizations waiting to be discovered? The discovery of exoplanets, planets orbiting stars outside our solar system, has opened up a new realm of possibilities. Some of these exoplanets exist in the habitable zone of their stars, where conditions might be right for liquid water and potentially life. Could there be alien civilizations with their own cultures, technologies, and histories? The thought of making contact with intelligent extraterrestrial life is both thrilling and daunting. Until relatively recently, the search for life beyond Earth was largely confined to the realm of science fiction. Writers and filmmakers imagined distant worlds and alien beings, capturing our imaginations with tales of interstellar travel and encounters with the unknown. These stories, while fictional, have inspired generations of scientists and explorers to look beyond our planet and consider the possibilities that lie among the stars. We simply didn't have the technology to detect planets orbiting other stars, let alone search for signs of life on them. Early telescopes, while revolutionary for their time, were limited in their capabilities. It wasn't until the development of more advanced instruments and techniques that we began to uncover the true nature of our universe. The invention of the spectroscope, for example, allowed scientists to analyze the composition of distant stars and planets, providing crucial insights into their potential habitability. But in the past few decades, thanks to incredible advances in astronomy and space exploration, we've entered a new era of discovery. Modern space telescopes, such as the Hubble Space Telescope and the Kepler Space Telescope, have revolutionized our understanding of the cosmos. These instruments have allowed us to peer deeper into space than ever before, revealing the existence of thousands of exoplanets and providing valuable data on their characteristics. Space probes and rovers have explored the surfaces of other planets and moons in our solar system, searching for signs of past or present life. We now know that planets are incredibly common in the universe, and we're finding more and more planets that resemble our own in size and temperature. The discovery of Earth-like exoplanets has fueled the hope that we might one day find a world with conditions suitable for life. These planets, located in the habitable zones of their stars, offer the best chances for finding liquid water and potentially life as we know it. The search for these planets is a meticulous and ongoing process requiring the collaboration of scientists and engineers from around the world. The search for another Earth is no longer a pipe dream. It's a scientific endeavor well within our reach. With each new discovery, we come closer to answering the profound question of whether we are alone in the universe. The data collected by modern telescopes and space missions is analyzed by teams of dedicated scientists who use sophisticated algorithms and models to identify potential habitable planets. As our technology continues to advance, so too does our ability to explore the cosmos and uncover its many secrets. The journey to find another Earth is just beginning, and the possibilities are endless. The quest to find exoplanets, planets orbiting stars other than our sun, has become one of the most exciting and rapidly evolving fields in astronomy. Astronomers have developed a variety of ingenious techniques for detecting these distant worlds, each with its own strengths and limitations. One of the most successful methods is the transit method, which looks for tiny dips in a star's brightness caused by a planet passing in front of it, blocking a small fraction of its light. Imagine a fly buzzing in front of a car's headlight. You might not see the fly itself, but you'd notice the momentary flicker in the light. By carefully measuring these subtle changes in starlight, astronomers can infer the presence of an orbiting planet, estimate its size, and even determine the length of its year. Another powerful technique for finding exoplanets is the radial velocity method, also known as the Doppler wobble method. This method has been instrumental in the discovery of many exoplanets since it allows astronomers to detect planets that are otherwise invisible. By observing the subtle movements of a star, scientists can infer the presence of a planet orbiting it. This technique has been particularly useful in identifying large planets that are close to their host stars, but advancements in technology are making it possible to detect smaller, Earth-like planets as well. This method relies on the fact that a planet's gravity tugs on its host star, causing the star to wobble slightly as the planet orbits it. The gravitational pull of the planet creates a small but measurable effect on the star's motion. This wobble is not something we can see with the naked eye, but with precise instruments, astronomers can detect these minute changes. The larger the planet, the more significant the wobble, making it easier to detect. This wobble, though tiny, is detectable as a shift in the star's light spectrum. When the star moves towards us, its light waves are compressed, causing a blue shift. Conversely, when the star moves away, the light waves are stretched, resulting in a red shift. These shifts in the light spectrum are known as Doppler shifts, and they provide crucial information about the star's motion and, by extension, the presence of an orbiting planet. As the star moves towards us, its light is slightly blue shifted, and as it moves away, its light is slightly red shifted. These changes are incredibly subtle, but with advanced spectrographs, astronomers can measure these shifts with great precision. By analyzing the pattern of these shifts over time, scientists can determine the presence of a planet, its mass, and even the shape of its orbit. This method has been a cornerstone in the field of exoplanet discovery. By carefully measuring these Doppler shifts over time, astronomers can infer the presence of an orbiting planet, estimate its mass, and even determine the shape of its orbit. This data is invaluable for understanding the characteristics of these distant worlds. The radial velocity method has not only helped in discovering new planets but also in studying their atmospheres and potential habitability. It has opened a new window into the universe, allowing us to explore worlds beyond our solar system. These techniques, along with others like gravitational microlensing and direct imaging, have revealed a staggering diversity of exoplanets. Each method has its strengths and limitations, but together they provide a comprehensive picture of the variety of planets that exist. Gravitational microlensing, for example, can detect planets that are far from their host stars, while direct imaging allows us to see planets directly, albeit with great difficulty. The combination of these methods has expanded our understanding of planetary systems, from gas giants larger than Jupiter, which are often the easiest to detect due to their size and gravitational influence, to rocky worlds smaller than Mercury, which present a greater challenge but are no less fascinating, orbiting their stars in a dazzling array of configurations. Some planets have highly elliptical orbits while others are nearly circular. Some orbit close to their stars, experiencing extreme temperatures, while others are in the habitable zone, where conditions might be right for liquid water. The diversity of these worlds is a testament to the complexity and wonder of our universe. Each discovery brings us one step closer to understanding our place in the cosmos and the potential for life beyond Earth. One of the most prolific planet-hunting missions to date has been NASA's Kepler Space Telescope, launched in 2009. Kepler stared at a single patch of sky for nearly 4 years, continuously monitoring the brightness of over 150,000 stars, searching for telltale transits that would betray the presence of orbiting planets. Kepler's mission was a resounding success, discovering over 2,600 confirmed exoplanets and thousands more candidate planets awaiting confirmation. Kepler's data revealed that planets are incredibly common in the Milky Way galaxy, with most stars hosting at least one planet, and many harboring multiple planet systems. Kepler's discoveries revolutionized our understanding of planetary systems, and paved the way for future missions designed to study these distant worlds in even greater detail. While most exoplanet discoveries to date have relied on optical telescopes like Kepler, radio astronomy is starting to play an increasingly important role in the search for worlds beyond our solar system. Radio telescopes offer a unique window into the atmospheres and magnetic fields of exoplanets, providing clues about their composition, habitability, and potential for hosting life. For example, radio observations can detect the presence of certain molecules in an exoplanet's atmosphere such as water vapor, methane, and carbon dioxide, key ingredients for life as we know it. Radio telescopes can also detect radio emissions from an exoplanet's magnetic field, which acts as a shield, protecting the planet's atmosphere from being stripped away by the stellar wind, a stream of charged particles constantly flowing from the host star. The combination of optical and radio astronomy is ushering in a new era of exoplanet exploration. By combining data from telescopes across the electromagnetic spectrum, astronomers can build up a more complete picture of these distant worlds than ever before. We're no longer limited to simply detecting exoplanets. We're starting to characterize their atmospheres, study their magnetic fields, and search for signs of life. The quest to find another Earth is a long and challenging one, but the pace of discovery is accelerating, and the future of exoplanet research is brighter than ever. With each new discovery, we're getting closer to answering the age-old question: are we alone in the universe? As we've journeyed together through the fascinating world of radio astronomy, we've seen how these invisible waves have revolutionized our understanding of the cosmos. We've peered into the hearts of distant galaxies, witnessed the birth and death of stars, and even glimpsed the faint afterglow of the Big Bang itself. Radio waves have allowed us to see the universe in a whole new light, revealing hidden wonders and unlocking secrets that were once beyond our grasp. Remember, our exploration of the universe is a symphony of discovery, with each new observation adding a note to the grand cosmic composition. Radio astronomy has given us a deeper appreciation for the vastness and diversity of the universe, a universe teeming with strange and wonderful objects that defy our imagination. From the rhythmic pulses of pulsars to the powerful jets of quasars, the universe is alive with activity, and radio waves provide a front-row seat to this cosmic spectacle. The future of radio astronomy is bright with promise. As technology advances, we're building even more powerful radio telescopes, capable of detecting fainter signals and probing deeper into the cosmos than ever before. These next-generation instruments will undoubtedly lead to new and groundbreaking discoveries, further expanding our understanding of the universe and our place within it. So, the next time you gaze up at the night sky, remember that there's more to the universe than meets the eye. Beyond the familiar twinkle of starlight lies a hidden world of radio waves, whispering tales of cosmic wonders. Keep looking up, keep asking questions, and keep exploring the universe around us. Thank you for watching Time Pilgrimage, and as always, please remember to subscribe and like. If there is a topic that you would like to explore, please drop a comment.